before we do some more examples of instantaneous rate of change and finding the derivative using limits, I want to give you some new vocabulary words and remind you of those definitions from last time. So we said that average rate of change, I have my formula in purple down here, is change in y over change in x. And last time we said that this is a slope. This is a slope of a line that goes through 2 points on the graph of a function. We call that line a secant line. Average rate of change is slope of a secant line. Now, instantaneous rate of change, we computed using this limit definition. And the instantaneous rate of change we said was the slope going through just 1 point. And that would actually be a line that's just touching the graph of the function at just 1 point. We call that a tangent line. So the instantaneous rate of change is the slope of the tangent line. We gave the instantaneous rate of change another word. We also called it the derivative. Okay, so let's do some examples. Example 2, consider the function f of x equals negative x squared minus 2x. Find the equation of the secant line that passes through points. Oh, this should say where. Sorry about that. Where x equals negative 2 and x equals 1. A secant line is a line that goes through 2 points, and the slope of a secant line is the average rate of change, or just change in y over change in x. So the first thing I'm going to do in this problem is I'm going to try to compute the slope by taking change in y. I'm going to call that f of 1 minus f of negative 2 divided by my change in x, 1 minus negative 2. Now f of 1, if I plug 1 into the original function that was given to me, I end up with a negative 1 minus 2, or negative 3. And f of negative 2, if I plug negative 2 into that original function, let's see, negative 2 squared is 4, so negative 4, and then that would be a plus 4, that is 0. So my change in y is going to be negative 3 minus 0, and my change in x is a 1 minus a negative 2, or 1 plus 2. So negative 3 over 3 is negative 1. The slope of this line is negative 1. Now, if I want to write the equation of the line, and that's what this problem is asking me to do, I'm halfway done. I know the slope. And so to find the equation of this line, I'm going to use something called the point slope formula. This is the point slope form of a line. I like using this formula to write equations of lines, but if you have learned another technique from previous courses, you are welcome to use it. In this formula, it basically says you just plug in the slope, which we computed for m, and then you pick one x and y value to plug in for the x1, y1. So my slope, my m is negative 1, and I am going to choose x equal 1 to be my x1, and so then negative 3 would be my y1. Plugging that into the formula, I get y minus negative 3 equals the slope, negative 1, x minus x1, which is 1. So that would be y plus 3 equals negative 1 times x minus 1. You can leave your answers in point slope form if you want. This answer is perfectly fine. If you'd like to solve this for y, you are welcome to. If I wanted to solve this for y, I would distribute the negative 1, and then I would subtract the 3. And so y equals negative x minus 2 would also be a correct answer. But again, I don't care if you leave your equations in point slope form or if you solve them for y. You can choose how you want to write your equations. So to summarize, to find the equation of a secant line, the slope was the average rate of change. We did that first. And then we plugged that slope and one of our points into the point slope formula. Now let's do the exact same thing, except we're going to find the equation of a tangent line this time. So same function. And now we are just looking at one point, the point x equal 1. What is the equation of that tangent line? So just like in the last problem, the first step is slope. However, unlike the previous problem, to find the slope, I have to now find an instantaneous rate of change. So I'm going to be computing the limit as h goes to 0 of f of 1 plus h minus f of 1 all over h. F of 1 plus h means we take the 1 plus h, we plug it in for x into that function. And I'm going to go through, get rid of parentheses. 1 plus h squared should be 1 plus 2h plus h squared. I FOILed that out. You can see an example of that in the part 1 of this lesson. And then let's see, we've got a minus 2 minus 2h. So minus 1 minus 2h minus h squared minus 2 minus 2h. And if I combine like terms, that would be a negative 3 minus 4h minus h squared. So all of that is my f of 1 plus h. F of 1, I plug 1 into the function, and that is negative 3. So my f of 1 is negative 3. So now my slope is limit as h goes to 0 of negative 3 minus 4h minus h squared minus a negative 3 all over h. If I combine like terms in the numerator, the negative 3's cancel out, and I'm left with negative 4h minus h squared over h. We've got a common factor of h in the numerator. I can factor the h out of the numerator, and now I can actually cancel an h out of the top and the bottom. So I'm left with limit as h goes to 0 of negative 4 minus h. If I plug in 0 for h, I'm just left with negative 4. So the negative 4 is my slope. That's my instantaneous rate of change, or slope of the tangent line. So finally, I'm going to use that same formula as last time. I'm going to use my point slope formula. Our slope, our m, is negative 4. I'm going to use negative 3 as my y1, and I'm going to use the x value 1 as my x1. Plugging that into the formula, I get y minus negative 3 equals negative 4 times x minus 1. I am going to write that as y plus 3 equals negative 4 times x minus 1. Now earlier I said instantaneous rate of change is the exact same thing as finding the derivative. And you can actually express your derivative or your instantaneous rate of change as a function. In other words, you don't need to have a number to plug in for x. So if I want to find the derivative of a function, again, I'm finding an instantaneous rate of change, and I'm going to use that limit definition. But this time, instead of using that letter a or an x value, I'm just going to use the letter x. In other words, I'm thinking of my instantaneous rate of change formula as the limit as h goes to 0 of f of x plus h minus f of x all over h. So I don't have a's, I have x's. So for my first example, where the function is 1 over x, our f of x plus h is going to be 1 over x plus h. Our f of x is just the original function, 1 over x. Plugging those into my limit definition, I get limit as h goes to 0 of 1 over x plus h minus 1 over x all over h. Now to evaluate this limit, we have to do some simplifying. And to simplify, I'm going to multiply everything by the LCD, which in this case is x plus h. So I'm going to multiply both terms in the numerator, and I'm going to multiply the denominator by that LCD. In the numerator, when I multiply that first term by x plus h, the x plus h's cancel, and I'm just left with an x. When I multiply the second term, the 1 over x, by the LCD, the x's cancel, and I'm left with an x plus h. I am just going to rewrite the denominator as h, x plus h. Now I'm going to distribute that negative sign in the numerator. So now I have a negative x and a negative h in the numerator. When I combine like terms, the x's cancel out. And all I'm left with in the numerator is the negative h. Nothing has happened to the denominator yet. Finally, I can cancel an h out of the top and the bottom. And I'm left with limit as h goes to 0 of negative 1 over x plus h. To finish my limit, I plug in 0 for h, so I get negative 1, basically x times x, or negative 1 over x squared. And that's my answer. That's the derivative of this function. Or another way of thinking about this is a formula that gives us the instantaneous rate of change at any time period or any x value. You could plug in specific x values to get a slope of a tangent line at a specific point or an instantaneous rate of change at a specific point. Let's do one more example of the same type of problem. I'm going to find the derivative, or in other words, I'm going to find a function that gives me the slope of the tangent line at any x value for f of x equals square root of x. So I've written down my instantaneous rate of change formula. And so in this case, f of x plus h, if I replace the x with an x plus h, I get square root of x plus h. That's my f of x plus h. And my f of x is just the original function. So plugging those things into my formula, I have limit as h goes to 0 of square root of x plus h minus square root of x all over h. Now to find this limit, we're going to use a trick we learned in one of the previous sections. I'm going to rationalize the numerator, and I'm going to do that by multiplying both the top and the bottom by the conjugate. In other words, I take that radical expression and I just change the sign. I do this because now I can actually use my difference of squares formula in the numerator. So that's going to give me limit as h goes to 0 of x square root of x plus h squared minus square root of x squared. That's my a squared minus b squared, my difference of squares formula. And then I'm just going to copy down that denominator. I'm not going to do anything with that yet. When you square a square root, those are inverse operations. That gets rid of the square root. So we have some like terms in the numerator. We can cancel out those x's. And so the only thing I'm left with in the numerator is an h. And then finally, I can cancel an h out of the top and the bottom. And now I just have a 1 in the numerator. And my denominator is square root of x plus h plus square root of x. Finally, last step, plug in 0 for h, and I get 1 over square root of x plus square root of x. This can also be written as 1 over 2 square roots of x. And that's my final answer. Again, this is an expression that really gives us the slope of the tangent line at any x value. If you plugged in a specific number for x, that would give you the slope at that specific location. So finally, I've got one more topic to mention, and that is when can you find derivatives? When can you find tangent lines, basically? And I have written down 3 different conditions, 3 different cases where a derivative would not exist. These are places where you cannot draw tangent lines, or you can't find the slope of the tangent line. So anytime you have a discontinuity, a jump, a hole, a gap in the function, you cannot find the derivative. In my example, that happens at x equals 5. The function is not continuous, and so the derivative doesn't exist at x equals 5. Now, the second kind of place where you can't draw a tangent line is if you see a sharp point or a corner. In this graph, that happens at x equals 4. So at x equals 4, the derivative doesn't exist. And then finally, if your function has a vertical tangent line, you can't find the derivative. And the reason is if you have a vertical line, the slope is undefined. That doesn't occur anywhere in this graph. So example 4, for the graph below, determine whether the derivative exists. In this particular graph, the derivative exists everywhere except at x equals 4 and x equals 5. All right, there's a lot of material in this section. It's pretty important stuff, so please don't hesitate to ask if if you're struggling with any of these problems.